Welcome to the Stellar Aerospace Universe channel. Be sure to subscribe and support the channel as we delve into the mysteries of the cosmos. Today we're taking a closer look at a concept that dominates every aspect of our lives, yet remains shrouded in mystery: time. In the realm of physics, time is simply what a clock reads. It's a fundamental quantity that weaves itself into the fabric of our universe, intertwining with other physical quantities to give birth to concepts such as motion and kinetic energy. But time is far more than just the ticking of a clock. It's a dimension, a constant, a river that flows ceaselessly, carrying with it the whole of existence. In the next few minutes, we'll journey through the fascinating evolution of our understanding of time, from basic definitions to complex concepts like space-time and atomic clocks. So, buckle up and prepare for a trip through the fourth dimension. Time, as we understand it today, has evolved dramatically from our ancestors' concepts. Our earliest predecessors measured time by observing the regular cycles of nature, the changing seasons, the phases of the moon, the rising and setting of the sun. They developed simple yet effective devices like sundials and water clocks to keep track of the passing hours and days. As our understanding of the universe expanded, so too did our methods of timekeeping. The pendulum clock, a marvel of the 18th and 19th centuries, was a significant leap forward in accuracy. Yet it was still not perfect, vulnerable to environmental changes and mechanical wear. The pinnacle of timekeeping, as we know it today, is the atomic clock. So what's so special about these atomic timekeepers? Well, they're based on the vibrations of atoms, specifically the energy transitions within atoms. Atomic clocks, like those at the National Institute for Standards and Technology, use hydrogen atoms which emit a specific frequency of light. The clock then counts the cycles of oscillation in that light to keep time. It's a process so precise that these clocks can keep accurate time for millions of years. But the atomic clock isn't just a triumph of human ingenuity, it's also a testament to our deepening understanding of the universe. Time, it turns out, is intimately connected to the very fabric of reality. Atomic timekeeping is our best tool for measuring this fundamental quantity, giving us the most accurate ticks and tocks to structure our world. So atomic clocks give us the most accurate measure of time, but did you know that time isn't absolute? It can be influenced by factors such as gravity. To truly understand time, we need to explore the groundbreaking theories of one of the greatest minds in history, Albert Einstein. Einstein changed the game when he introduced his theory of relativity, which essentially told us that time is not an absolute constant, but rather a relative concept that can change based on where you are and how fast you're moving. Now, let's delve a bit deeper into this. Einstein proposed that time is intertwined with space in a four-dimensional structure known as space-time. Before this, space and time were considered separate entities, but Einstein tossed that idea out the window. In the world of space-time, time coordinates depend on both time and space coordinates of a moving system. This means that time can change depending on where you are and how fast you're moving. This brings us to another fascinating concept that comes from Einstein's theory of relativity: time dilation. Time dilation is the difference in elapsed time as measured by two observers due to a difference in their velocities or gravitational potentials. So if you're moving at high speeds or near a massive object like a planet, time would actually slow down for you compared to someone who is stationary or away from such massive objects. This isn't just theoretical, mind you. Time dilation has been confirmed by various experiments, and it's even taken into account in systems like GPS. Without correcting for the time dilation effect caused by Earth's gravity, GPS systems would be off by about 7 kilometers per day. Einstein's theories introduced us to a world where time can stretch and slow down. But could it also allow us to travel through time? Time travel has been a popular theme in science fiction, but is it possible in reality? According to physicist Albert Einstein's theory of special relativity, time is relative to the observer's speed. This means that time passes more slowly for objects moving at high velocities. It's not quite the time-traveling DeLorean from Back to the Future, but it's a start. Interestingly, this phenomenon has been observed in astronauts who spend time in orbit. They age slightly slower than their counterparts here on Earth due to the high velocities at which they're traveling. It's a small effect, but it's there. But it's not just speed that affects time. Einstein's theory of general relativity states that time is also affected by gravity. Clocks positioned closer to large gravitational masses like planets or stars tick more slowly than those situated further away. This is why GPS satellites, which are far away from Earth's gravitational pull, experience a time dilation of about 38 microseconds per day. Theories about time travel often involve wormholes, a sort of shortcut through space-time. If a wormhole could be stabilized, it could theoretically allow for time travel. However, no real-life wormholes have been identified, and the energy required to create and sustain one would be astronomical. While time travel remains largely within the realm of science fiction, our understanding of time continues to evolve, bringing us closer to the answers. From the tick-tock of a clock to the bending of space-time, our journey through the concept of time has been truly fascinating. We started by looking at the fundamental definition of time in physics, a concept that has evolved from the regular recurrences of seasons to the atomic precision of modern clocks. We then delved into the world of atomic clocks, marvels of technology that keep accurate time for millions of years and are integral to systems like GPS. We explored how time is not absolute, but can stretch and slow in the presence of gravity and the expansion of the universe, leading us into Einstein's groundbreaking theory of space-time. Space-time, a concept that merges space and time into a four-dimensional continuum, showed us that time isn't just a river flowing at a constant rate, but a dynamic entity influenced by space and gravity. This brought us to the intriguing concept of time dilation, where time can appear to tick slower due to relative velocity or gravity. Finally, we ventured into the realm of time travel, a tantalizing prospect supported by scientific theories, yet still largely confined to the pages of science fiction. We discussed how time dilation could potentially allow for future time travel, and how time's unidirectional flow is still one of its greatest mysteries. Thank you for joining us on this journey through time. Don't forget to subscribe, support, and share our content. If you have any questions or thoughts, drop them in the comments below. Until next time, keep looking up and wondering about the mysteries of the cosmos.